Hello, fellow neuroimagers. Today we're going to cover the 07 lab. This one was a bit of a doozy, so I'm going to hopefully demystify it for you here. So we open up the terminal, and as we always start out, we're going to cd to the labs repository, and we're going to start up our Jupyter notebook. Even though we will mostly be working in the terminal still, but it'll be helpful to read the directions and see what we're getting stuck on. Okay. Already took care of that, already downloaded the data. And now we'll get set up with the FSF file. So when we start this, we'll click on the feet fMRI analysis. And we want it to be first level since we're still doing the subject level. And since Michelle already loaded up an FSF file for us, we can load that up, or what I did instead was already change the paths, but I'll still walk through it here. But I already changed the paths to my specific data set. So I named that one _jk.fsf. So I'll load that one up. And I'll still walk through everything as if I was setting it up through the first time, just so you can see. So select the 4D file. As you can see, it points to the flanker bold file that is defined in my specific path. But to select that file, all I did was click on the select input and click on that. Hit OK. OK. And we're good. Then for the output file, click on this right next to the output directory. And again, we'll see that this follows the path to the directory where we are, and at the very end we have filtered typed out. So everything will go into eventually a filtered.feet directory. And total volumes, we're not going to delete any of the volumes. You might want to do this if your scanner doesn't throw out dummy scans. We did, for this experiment, have the scans, a couple of the first acquired scans throw out, because as I was speaking in class today for the other 08 lab, sometimes the first couple scans in an MRI scanner, the magnetic field hasn't homogenized, and there can be some high signal intensities that can bias the overall course of the MRI time series. And then the TR is 2 seconds, that's derived for us, and we'll keep the default for the high pass filter. Prestats, going to keep everything as the default. We're going to use brain extraction. We're not going to do slice timing for this. Motion correction, going to use flirt. Spatial smoothing is going to use 6 millimeter kernel, and we will use our high pass filter, and we will not use melodic data exploration. So that's all I have to look for the prestats tab. Now moving on to the registration. The main structural image is just going to be our brain, and then to transfer it to standard space, we have the M&I brain listed in the standard location where FSL is installed. And again, if I was to select this file, I'll just select it like by clicking on the little folder next to it, and then clicking on the file name that I want to select, and then OK. And again, for brevity, we are not going to do a nonlinear registration from our anatomical to standard space to help shorten the time it takes to run this, because nonlinear registrations can take up to 20 minutes just on their own. So for the sake of brevity, we're just going to stick with a linear registration. Finally, on the stats tab, we're going to use film pre-whitening. So again, there can be autocorrelations between the volumes, and this can occur because of heartbeat, respiration, and anything else that can occur a little bit quicker than the 2-second interval in which we're collecting the data. And we're not going to include the motion parameters for this one, and we're not going to use any of these additional options, but we will look at the full model setup. So again, now that I have this FSF loaded, we get it all filled out for us. And the basic shape that we want is the custom 3-column format. And we want the double gamma HRF, because that is now standard to include that for most MRI analyses. We got to account for that post-stimulus undershoot that occurs as well, not just the main event of the bold rising. And again, to select the correct file, we click right here, or right here on the folder, but let's just make sure if we're on the con tab, so that means we want the congruent file. So we'll click there, and it's already in the directory for us. If we weren't in that directory, we would see it right here, EVs, and we would collect con_fixture.txt. Okay, and I can just scroll over here to see that is the file that I expect. And again, we do the same thing for neutral. Make sure we selected neutral. For incongruent, make sure we selected incongruent. And finally, the errors. So _fixture. Okay. So all those look right. Then we can switch over to the contrast and F-test tab. And we want to do this for the original EVs. And we will have 5 contrasts in total. The first 3 are just selecting averages. So again, to draw the relationship between, why are we calling this one con? Because EV1 is set to 1 and the rest are set to 0. If you look back to our EVs, EV1 is con. So it's congruent, and that is the only one that we have selected. Same for neutral. Neutral is the second one. So if you look back here, just to confirm, EV number 2 is our neutral. And when we look at the contrasts, when EV2 is the only one that has a 1 and the rest are zeros, then we know that we're measuring just the average activation of neutral above baseline. And then same for incongruent. And now for the interesting contrasts, we can look at where incongruent is greater than neutral. So we set neutral to -1, and third one, which is incongruent, to +1. Then we can do the same for incongruent greater than congruent. So again, the EV1 was congruent, so we set that to -1. And then EV3, which is incongruent, we set that to +1. And then we can view the design to make sure it looks as we would expect. Looks fine to me. Then we can also see the efficiency. So for the effect required. So again, the percent, we can read this, but it should be the percent increase in the bold response in order to see an effect for that contrast. So I'll hit done on there. Again, it shows us that. We don't need to see that. And for the post-stats, we're just going to use all the defaults, except I'm going to unclick this one. Sometimes that can take a very long time, and it doesn't always it can give sometimes useful results. So if you're debugging something, it might be useful to have this on just to see if the time series plots will fit your expectations. But for the sake of this lab, I think I'm going to turn it off for the sake of time as well. So again, all this looks good. So if I was just making this and hadn't saved it yet, or I did make that change in post-net, so I'll hit save. And again, I added the underscore JK, so I don't have to add that again since I already added it in last time, but I can see what the file name will be for my output file. Hit OK to save, and then we will be ready to run. So to run it, we'll just hit the go here. And I will pause the video so that we don't have to look at this run for the next 10 minutes. And again, this was just the analysis that we ran through during the lab. So the next one will be how we change it for the first homework problem. Alright, so I'm going to pause here, and I will pick up as soon as we are ready to move on. Alright, so we're back, and now we can see the output from the feat script that we just ran. So again, if it ran correctly, it should look something like this. It'll show the processing stage 1, registration, processing stage 2, stats, and yep. Then it should go all the way down to the thresh zstat 5, which is our 5th contrast that we defined, which I believe was the incongruent greater than congruent contrast. Again, we can see that the file that we're reading from actually exists in our directory. So if we went to labs.jdcat, 07 lab, filtered feat, report underscore log.html, if we open that file, we would get this same view. So we can click around and look at some of the results that we might see. Looks like we get some results for the greater than baseline. Doesn't look like we get any results from there, so if we click on it, it'll tell us which globs we get results from, or whether it'll characterize the blobs as homogeneous clusters, and it'll give us a summary statistic of each of those clusters. So again, so we see here cluster index, number of voxels, how significant it was, and it'll even give us the max coordinate and the center of gravity coordinate. So this is the most central portion of the blob of voxels that it saw. So we can see all that information from there. And again, we can just follow this this file up here to see exactly which HTML file that we're reading from. And we can go to stats. We'll see the design. Pre-stats, where you can look at some of the motion estimates. Then registration, where we will see how well the registration went. Func to high res, okay. Looks like we did an okay job getting the functional to high resolution space. And with linear, we can't expect much. And that is it. So just to show that you can open up this HTML file again, I will do that for you here. So Control-Shift-T to open up a new one. CD into 07 lab. We'll CD into filtered feat. And what we will do is XDG open, and this will just choose the default application to open the file based on its extension. So I can do report.html. And that takes me to the main page in which I can click on any of the subsequent processes or the subsequent categories that I looked at before. Perfect. So now close this one. We don't need that anymore. Go back to here. All right, and what we need is this. Okay. So for the first homework, we were asked to determine if using task regressors that account for the trial reaction time change the results. So in order to do that, we need to use the RT-dir instead of the fixed-dir. So again, I already have an FSF file saved, and that one is called basicdesign_jk_rt. So if I load that one up, then that will have everything that I need. Again, this file should be the same, so the bold file will be the same. The output directory is now going to be changed, so I don't want to put it into the same directory, so I just did filtered_rt. And then the only other significant change comes from the full model setup, where again, for con, new, and inc, and errors, we used the fixed-dir before, but now we're using the RT-dir. And then again, these files have the reaction time instead of the fixed duration listed in the second column of the file. So again, this one's the RT-dir. This one's the RT-dir. So on and so forth. And that is the only real differences that were made here. All the contrasts are still the same. So the only things that I changed for this one were the for the full model setup, which files I put in, which were the RT-dir instead of the fixed-dir. And for data, on the data tab, I changed the output directory. And those were the only two changes that I made. So now with that all set up, we can hit go again. And again, this will take a few minutes, so I will pause here and pick it up. Alright, so we see that this feat run has now finished, so this is with reaction time. And again, we can look at the stats, or the post stats, to see what, if anything, has changed. So again, we can click on these. Looks like, just superficially, there is an additional cluster that was found for the congruent contrast relative to the baseline. And it looks like still nothing else has a quote-unquote significant cluster. And now that that's ran successfully, I'll leave some of the interpretation to you guys to compare the two. So again, I can open up the other one, or the other report, so I can compare them side by side. So again, I can do that with xdg open report.html. Okay, so we can go post stats here too. You can click on this. I can click on this one. So it looks like we probably added another small cluster. And all the clusters are generally appear to be a little bit larger for the congruent stimulus. Alright, but I can leave other visual modifications. Again, you can do something like a subtraction between the two Z maps. So that would look something like this. So I'll do FSL Maz. Let's say specifically you want to look at the fifth contrast. So we need to find our input image. So filtered dot feet, and then I will go to quit stats, and then zstat 5. I can do sub. Now filtered rt dot feet, stats, zstat 5. I can call this fix minus rt zstat 5.nai.gz. Then I can do an FSL view with that fix underscore minus rt. And I can see that there are some changes around here. Let's see if we can threshold this. See where the maximal changes are. We can get an idea by looking at the image histogram. So again, it looks to be mostly not a lot of differences. Looks like there's almost half a standard deviation in the negative direction, and I'm sure that this peak eventually goes out to the other side to see a plus half standard deviation. So we'll try to confirm that. If I set the minimum to 0.5 and the maximum to 0.8, let's see. Yeah, we can see some spots that still survive that threshold, but they are few. Let's try lowering this a bit. Yeah, we can kind of see a cluster around here that was modulated by reaction time. For the incongruent is greater than congruent contrast. So it looks like those two analyses methods turned out different results for this particular area. And then I can add our bold just so that we can see roughly where that is. So yeah, this almost looks to be a bit in the lower part of the insula. So yeah, again, I won't talk about everything that's between the two, but those are just some things that you can look for. So now we'll move on to the next part of the lab, where we are going to run pre-processing without high-pass filtering. So now, okay, don't need this. So what we are going to do is that I have an FSF set up for this one as well. So I'm going to load that one up, and it's called pre-ICA. I'm going to open that. So again, the changes we made is that this was at full analysis, and we changed it to pre-processing only. All the pre-stat stuff are the same, except the high-pass filter is not selected. And for registration, we now have the nonlinear registration selected as well. So again, this will take a while. So I'll pause the video and let that run. And I also changed the output directory to something called pre_ICA. So it'll put everything in the pre_ICA.feat directory, but the input file is still the same. Okay. So if we're good to go, again, if I wanted to save this file as something different from my previous FSFs, I would click on the Save tab, and then I'll change the name and how I wanted to save it right here. Right now I already named it _JK_pre_ICA, so that's already good, so I'll hit OK. And again, to run, I'll just hit go. And it will start running for me. Alright, now I'll pause the video again and wait for this to finish. Okay, and we're back. So now that the output from the pre-ICA-AROMA ran, and we got the nonlinear registration and the pre-processing done, that doesn't include spatial smoothing, now we're ready to move on to running ICA-AROMA itself. And since we have a feat directory, we can specify the feat directory with this -- feat command after we've called the ICA-AROMA.py file. And I do not want to have that extra feat there. And again, when we're calling this script, we're calling it relative to where this script is. So when we specify the feat, we need to go back a directory and specify the pre_ICA. And when we specify the output, which I'm just going to call aroma out, we also have to specify it in relationship to the directory that this script is located. So if I didn't have this double dot, meaning going back one directory, it would output it in the same directory that the ICA-AROMA script is located in. Okay, so now I can run this. Oh, can't do the double dash for out. I'm trying. Is feat and double dash? Guess we'll see. Nope, okay. Then I will do that. There we go. And now we'll let ICA-AROMA run, and we will come back when that is finished running. Alright, ICA-AROMA finished running, so now we're just on the last step that we need to run, which will be running feat with the denoised ICA-AROMA. So there's a couple changes that we need to make here. Again, I already had a loaded FSF file for jk_post _ICA.fsf. So I loaded that one up. And I'm going to select the input, which again from here I put in a folder called aroma_out. So when I hit select here, you see it's in aroma out and it's the denoised func data non-aggressive. So that's what we want to pass in. And then the output directory is going to be called post ICA, so that's where we're going to put all our post ICA results. And here we want to make sure that motion correction is set to none, since that's already been done. I believe brain extraction has already been done. Let's verify that real quick here. and we see that the skull's been removed, so we don't need to run bet again on the functional series. It's already been smoothed, so we can set that to 0, and that's the same as saying we're just not going to smooth. But we haven't done the filtering yet, so we will run the high pass filtering. Again, this is just going to be a linear transform that we do. Stats are going to be the same. It's going to be, yeah, it should all be fixture. So maybe that was set as our teeter from previous run. So I'll set all those to fixture. Okay. Otherwise, everything else should be the same once we've made the change to the input file, the output directory, and prestats, making sure we're not doing motion correction. Now we've set smoothing to 0, and that we do select the high pass filter. And that the anatomical will be the same, again, doing linear registration. And now that that is all set up, we can save it as our post ICA, just so that we have a model of that. And we will hit go. Then we'll let this run and finish up, and that will be the rest of this video. I will not walk through the comparisons of ICA-AROMA to the regular, since we already saw the methodology to do that. Again, you can just click on the stats or post stats tab and compare between the two and do some subtraction between the z statistics, and you can draw your own conclusions about how those compare to each other. Alright, thank you for sticking with me. That is the end of this video. Thanks for watching.